Hi, good afternoon, everyone. It is time to start the third talk of the PRISM uh, series number three, space instrumentation. In this talk, we are very glad to invite wait a minute, Professor Saito, Professor Saito from ISAS to give us some introduction about the space plasma particle measurement. Professor Saito is a very experienced on about the space plasma particle instrument, and we also have a lot of interaction in the past uh, collaborations. So in this talk, I was suppose everyone will be interested with this one because of space plasma particle measurement is important not only in atmospheric physics but also in magnetosphere measurement as well as planetary exploration. Okay, let's welcome Professor Saito's talk.
Okay, thank you very much, Alfred-san. My name is Yoshifumi Saito. I'm in ISAS JAXA, and I have been developing plasma particle instruments for nearly 30 years at ISAS. Okay, so today I will talk about the plasma particle measurements in space. And what we want to do is to understand the structure and dynamics of the terrestrial and planetary magnetospheres. And in order to do so, we make in situ measurements of plasma particles and magnetic electric fields and plasma wave and other measurements. And we develop science instruments and put them on a spacecraft and send the spacecraft to the area we want to make observation. So that is the in situ measurement. And for magnetosphere observation by satellites, we make observation using these instruments on spacecraft, including magnetic field and electric field and thermal plasmas and low energy charged particles, medium energy charged particles, and high energy charged particles, neutral particles, plasma wave, and optical measurements, including UV, EUV visible, and so on. And today I will talk mainly about charged particle measurement, especially low energy charged particles and high energy charged particles. And charged particle analyzers measure the number or current of the electrons or ions entering the analyzer. And the measurements are made with a fixed sampling time discriminating the energy, direction, and mass and charge state of the charged particles. And by using this analyzer, what we are doing is counting the electrons or ions one by one. And this figure shows the energy range of the charged particle measurements. And the energy range is separated into three energy regions. And one is low energy, and next one is medium energy, and the third one is high energy, starting from 1 eV to 100 mega eV. And at present, the techniques to measure each energy range is different. For example, low energy particles are measured using electrostatic analyzers, and time of flight mass spectrometer is used, and MCP or channel tone is used as a detector. And concerning the medium energy, the electrostatic analyzer and time of flight measurements and SSD and MCP are used. And for high energy particles, time of flight or SSD are used. And at present, those instruments for these three energy range is developed separately by separate groups. I hope in the future, the instruments to cover all the energy range will be developed. But anyway, at present, the different groups are developing so different instruments for different energy different energy ranges. Okay, and using the low energy analyzers, we can measure solar wind plasmas and magnetospheric plasmas, including lobe or plasma regions, and high energy particle instruments can measure the accelerated particles, including radiation belt particles. And medium energy range instruments are important in order to understand the acceleration mechanism from low energy to high energy. And first, I will talk about the low energy instruments. And the plasma analyzers covering low energy between 1 eV to 30 keV is categorized into two groups. One is energy spectrometer, and another is mass spectrometer. And energy spectrometer measures energy spectra of charged particles. And energy spectra is shown here. It is a line plot. The horizontal axis is energy, and vertical axis is flux or count. And there are several instruments in this energy for this energy spectrometers, including the instrument using electric field, that is electrostatic analyzer, and others are using magnetic field, and some of the instrument uses solid state detector if the measurement energy is high. And in these electrostatic analyzers or the analyzers using electric field, there are several types of instruments, including Faraday cap and spherical deflector or cylindrical deflector or electrostatic mirror and so on. And today I will mainly talk about the spherical deflector. And another category is mass spectrometer, and this measures energy mass spectra of charged particles. A mass spectra is shown here. That is a line plot. Vertical axis is flux, and horizontal axis is mass. And we also have several types of mass spectrometer. One is using electric field and magnetic field, and another is using AC electric field, and the third one is using energy measurement plus time of flight measurement. Okay, first I will talk about the principle of electrostatic analyzer. And this is the instrument to measure energy spectrum. And the simplest electrostatic analyzer is shown here. That is electrostatic deflector that consists of two metal plates. Those plates are parallel with each other. And ions or electrons can fly from the left-hand side to the right-hand side. And in case of ions, and applying positive voltage to the upper plate and negative voltage to the lower plate, then inside these plates, electric field is generated. The direction is from top to bottom. And the ions go into this electrostatic deflector, receive force from the electric field, and bend to the downward. And when the incident positive ion has low energy, it bends so much and collides with the bottom plate, and it is not detected. And if the energy of the incident ions is very high, it doesn't affected by the electric field so much. So go this way. And if we put the detector here that is sensitive to charged ions or electrons, then depending on the voltage applied to these two plates, the ions with appropriate energy is detected by this detector. So by changing the voltage applied to these two plates, we can measure the energy spectra like this. So this is the most simple electrostatic deflector. But actually, this cannot be used in space because usually this detector to detect ions or electrons is also sensitive to solar photons. So in the space, we have a solar light illuminating the instruments, and the number of the photons at the Earth's orbit is about 10 to the 12th per square centimeters per second. So that's too much. So we cannot use this simplest electrostatic deflector in space. So what should we do? One way is to bend the detector plates like this. And though this is the two-dimensional figure, but the shape of this electrode is three-dimensional, so it is a part of the sphere. And there is outer sphere here, an inner sphere here, and applying high voltage to the outer and lower sphere, outer and inner sphere, appropriate energy, the ions with appropriate energy can go through, pass through these two plates and detected by the detector placed here. And talking about the photons, it will go straight on and collide with the outer sphere first. And if we make the surface of this outer sphere to absorb these solar photons, the solar photon will not go to reach the charged particle detector, and this will function quite well in space. And this is called spherical deflector. And I will show you an example of the spherical deflector on the spacecraft called Geotail that was launched in 1992, so about 30 years ago, but still we are operating this spacecraft. And this right-hand side figure shows the orbit of this Geotail spacecraft. The thick line shows the moon orbit, that is, the distance between Earth and Moon is 60 times the Earth's radius. And the Geotail spacecraft first went to about 200 times the Earth's radius in order to measure the plasmas in geomagnetotail. And after that, the spacecraft perigee is about 10 RE and apogee is about 30 RE, and continue observation for more than 25 years. And on this spacecraft, there is an instrument called Geotail LEPEI and EAE, and this is the spherical deflector. And the cross-section of this instrument is shown here. And the photo I showed you is taken from this way, from this direction. And you looked at the outer sphere of this analyzer, ion analyzer part. And this instrument consists of two electrostatic analyzers. One is for ions and another is for electrons. And both electrons and ion analyzer has outer sphere and inner sphere. And in measuring ions, positive voltage is applied to the outer sphere and negative voltage is applied to the inner sphere. And in measuring electrons, a positive voltage is applied to the inner sphere and negative voltage is applied to the outer sphere. And changing the voltage applied to this inner and outer spheres, we can select the energy of ions or electrons. And this is the detectors called as CM or MCP. This is channel electron multiplier, and MCP is multi-channel plate. And this instrument is called 90 degrees spherical deflector or quadraspherical analyzer, because this angle of the electrode is 90 degrees, and this is the 1/4 of the sphere. And this looks like a watermelon. And using this analyzer, we can obtain this kind of data. And this figure shows the ET spectrograms. This is energy time spectrogram. And the horizontal axis of this diagram is time, and vertical axis is energy. And particle flux or count is shown by color code. And the bottom 4 panels are for electrons, and bottom 4 panels are for ions. And this data was obtained when the spacecraft crossed from lobe to the plasma sheet region. And as you can see, in the lobe region, we can see only a low energy ions flowing tailward. And as the spacecraft went into the plasma sheet, the hot ions and hot electrons are observed. So this kind of data can be obtained. And talking about the charged particle detector, usually we are using channel electron multiplier or microchannel plates. And we want to measure the charged particle one by one. And in order to detect single charge, charged particle multiplier is used, because one unit charge is the 1.6 times 10 to the minus 19 coulomb. That is too small number. So we have to multiply these charges using the particle multiplier. And channel electron is shown here. The size is about 1 centimeter times several centimeters. And when the charged particle enter into this device and applying high voltage between the inlet part and outlet part, when the incident particle collides with the inside wall of this channel electron, it generates secondary electrons and multiple secondary electrons. And those electrons are accelerated by the electric field and collides with the wall again. And repeating this collision between the collision of the walls, the incident electrons are multiplied to about 1 to 10 to the 7th. And 10 to the 7th electrons means 1.6 times 10 to the minus 12 Coulomb. So we can detect those electrons using the electronic circuit. And the bottom figure shows the MCP. This is the two-dimensional plate, and it consists of very thin tubes. And the structure of the tube is similar to this channel tone, and the electron multiplication principle is nearly the same. And applying high voltage between the surface and backside of this channel tone MCP, the secondary electrons are emitted, and it is multiplied. And using one plate, the thickness of 0.5 millimeters or 1 millimeters, the unit charge is multiplied up to about 10 to the fourth. And we want to multiply to around 10 to the seventh. We have to use multiple MCPs stacked together. Okay. And this is the circuit detecting the charged pulse. And when the charge enters into this channel tone and multiplied here, and the charge cloud is emitted from the output of this channel tone. And it is fed into operational amplifier, and capacitor and resistor is connected. So this is called charge amplifier. And this amplifier converts the charge cloud to the voltage pulse. And the number of the voltage pulse is counted by this counter. By doing so, we can measure how many electrons or ions come into this detector. And this figure shows the schematical figure of 90-degree spherical deflector. And there is an inlet part here, and the detector, this is channel tone or MCPs are here. And when the particles come perpendicular or normal to the inlet part, it flies like this, circular. It flies like this, the circular motion, and detected by this detector here. And if the particle come from this way, inclined to the normal direction to the inlet part, it also move circularly, with circular motion, and detected by this detector number 1. And if the incident direction is here, number 3, it is detected by this detector here, number 3. So the detected position reflects the incident angles, incident direction. And when we install this instrument on the spacecraft, it is installed on the sidewall of the spacecraft. And this spacecraft is the spinning spacecraft. And utilizing the spacecraft spin motion, we can cover the three-dimensional space. So using this instrument, we can measure three-dimensional charged particle distribution on the spacecraft. And this figure shows the spacecraft spin motion looking from the spin axis, and dividing the spin plane into, for example, in this case, for geotail case, 16 sectors. And in each sector, we'll change the voltage applied to the analyzer plate. And then during the one spin of the spacecraft, we have energy spectrum of ions or electrons with 16 times 7 directions, because this instrument has 7 channels perpendicular to this this figure. Okay, so by doing so, we can measure the three-dimensional phase space density, three-dimensional data of the electrons and ions. Okay, so I talked about the 90-degree spherical deflector. The cross-section is shown here. And as you can see, there is an incident area here, inlet part here. And when the particle come into this instrument, the incident area is largest. However, when the particle come into this instrument, inclined to the some angle between the normal direction of this instrument, the incident area becomes smaller, because we have to multiply cosine angle between this normal direction and the incident direction. So this means that the sensitivity of each channel is different using this 90-degree spherical deflector. That is not ideal characteristics, So this kind of instrument called top hat type electrostatic analyzer is developed. And this instrument shows the shape that the top of the outer sphere is cutted out, and the hat is placed. So this shape, from this shape, it is called the top hat type electrostatic analyzer. And charged particle come into this way, and flying like this, and detected by the detector placed at the bottom of the instrument. And because this instrument has this axis symmetric shape, so this instrument has the 360 degrees field of view, and coming into any direction, the sensitivity of the instrument is the same. So that is the very good characteristics. So at present, most of the space plasma instrument, low energy space plasma instrument has this shape using this top hat type electrostatic analyzer. And MCP plus MCP anode is used for this, usually used for this top hat type electrostatic analyzer. And we have to decide the position of the multiplied electrons or ions at the exit of this analyzer in order to identify the incident direction of the particles. And by doing so, in order to do so, we need the MCP and the MCP anode below that. And MCP anode is a metal plate divided into multiple sectors, and that number of the sector decides the angular resolution of this instrument. Okay, I'll show you one example of this top hat electrostatic analyzer, and that is the on the spacecraft Arase that was launched on 20th December 2016. And this is the photo of Arase spacecraft in ISAS on the vibration table. And this is an electron, low energy electron analyzer on Arase spacecraft. And this is developed by Kazama-san in Taiwan. And this is the top hat type electrostatic analyzer here. And preamplifier and MCP is, detector MCP is here, multiplier is here, and also MCP anode is here, and preamplifier is here, and high voltage power supply to supply voltage to the detector and analyzer plate is here. And using this instrument, this kind of ET spectrogram that is very beautiful is obtained. Okay, so this is the example of the data. And another example is electrostatic analyzer on Bepi Colombo Mio. This spacecraft is to measure Mercury magnetosphere, and it was launched in October 2018, and it is now on its way to Mercury. And it will arrive at Mercury in December 2025, so 4 years from now. And this is the Mercury ion analyzer. This is also an electrostatic analyzer that is top hat type electrostatic analyzer. And it measures ion energy spectra. And the right-hand side figure shows the cross-section of this analyzer. This is the top hat type electrostatic analyzer. But in case of Mercury, we have to measure high solar wind ion flux and low magnetospheric ion flux altogether. So the instrument has to a wide dynamic range as wide as 10 to the 7th. And usually the dynamic range of MCP or channel tone is 10 to the 4th. So we have to manage 10 to the 3rd dynamic range using the structure or operation of this instrument. So in this case, we use electrical sensitivity control by applying high voltage to the stop cap part. And by applying high voltage, by changing the applied high voltage, we can reduce the geometrical factor down to about 1%. And another way is to using mechanical attenuation grid. And in this case, about 1/3 of the entrance part, we put this mechanical attenuation grid. And using this attenuation grid, the incident flux is reduced to about 10%. So using both this mechanical attention grid and electrical sensitivity control, the 1 to the third dynamic range is realized using one instrument. And another characteristic is that this analyzer uses a very small amplifier included in this ASICs. And the size is 5 millimeter times 5 millimeters. And inside this small chip, the 64-channel amplifier and counters are included. So this contributes to reduce the power and size of this instrument. Okay, so next I'll move on to the mass spectrometer. And mass spectrometer measures energy mass spectra of charged particles. And I will show an example, a mass spectrometer that utilizes the energy measurement plus time of flight. And this is an example of the mass spectrometer. This is also an instrument on Arasse spacecraft. And this is a LPI instrument. And as you can see, it consists of electrostatic analyzer, ESA, and time of flight section, and MCP and preamplifier and electronics circuit boards. And looking at the cross-section of this instrument, we can see a top hat type analyzer here and MCP detector here. And between MCP and a top hat type electrostatic analyzer, we can see this section. This is the time of flight mass analysis section. And zooming into this section, we can see that what we have to do is to measure the time of flight of ions between here and here. We know the distance from here to here as L. And what we have to do is to measure the timing that the ion passed through this ultra-thin carbon foil placed here and detected by this MCP. And when the ions, energy selected ions, collide with this very ultra-thin carbon foil, the secondary electrons are emitted here, like this. And secondary electrons are accelerated and detected by the MCP at this position. And this is used as start signals. And because this is a very thin carbon foil, the incident ions can pass through this carbon foil and go straight on and detected by this MCP here. And this signal is used as stop signal. And detecting the time difference between start signal and stop signal, we can know the velocity of these ions flying from here to here, because we know the distance L. So L divided by T, flight time, is the velocity. And this top hat type electrostatic analyzer can measure the energy per charge. So by using this energy per charge information and the velocity information, we can decide the mass of the ions. So this is the principle of this time of flight mass spectrometer. And using this instrument, this type of ET spectrograms was obtained, separated from the mass species are separated. This is the hydrogen, and this is the oxygen, and this is helium, and so on. So we can obtain the mass discriminated ET spectrograms using this instrument. Okay, another example is the mass spectrometer on Kaguya spacecraft. Kaguya was a Japanese moon orbiter launched in 2007. And right-hand side photo shows the ion mass spectrometer. And by using this instrument, we obtained these ET spectrograms around the moon. The altitude was 100 kilometers. And from here to here is 2 hours. That is one revolution of the spacecraft around the moon. And we can see these ions coming from the moon. And there are several species of ions here. One is solar wind protons scattered at the lunar surface. And solar wind ions are here and here. And another pickup accelerated ions are also observed like this. So by measuring this, we can understand from where the ions come from. And because this is the mass spectrometer, we also have the mass spectrum like this. The horizontal axis is time of flight, but this corresponds with the mass of the ions, and vertical axis is the count. And we can see that we have a potassium and sodium peaks, And this is the first data obtained at 100 kilometers around the moon. And this figure shows the cross-section of this instrument. And because the Kaguya spacecraft was three-axis stabilized spacecraft, one surface of the spacecraft always facing the moon. But what we want to do is to measure the three-dimensional distribution of ions. So this kind of instrument has to very wide field of view. For example, this instrument has a hemispherical field of view by using these electrodes here, and by applying high voltage to the electrodes here, we can change the incident direction of the ions. And inside the analyzer, we have these spherical deflectors, nearly the same as top hat type electrostatic analyzer, but it is 45 degrees inclined. And by this electrostatic analyzer, energy per charge is selected and go into the mass analysis part here. And this is called the LEF, linear electric field type time of flight mass analyzer. And there is a very thin carbon foil here. And so, when the ions go into this carbon foil, because carbon foil is very thin, it is passed through this carbon foil. And ions are reflected by the electric field. The intensity is proportional to the distance from the carbon foil, and it is reflected like this. So the motion of this reflected ion is the sinusoidal motion, that is the same as the spring motion. And the reflected ions collide with the top part of this instrument and generate secondary ions. When the ions pass through this carbon foil, secondary ions are emitted. So measuring the time difference between the secondary electrons emitted when the ions pass through the carbon foil and the electrons emitted when the ions collide with the top part, we can measure the time of flight of these ions. And by this measurement, we can determine the mass of these ions with very high mass resolutions. Okay, so these are the example of mass spectrometers. Next, I move on to the high energy particle instruments. This is an example of the high energy electron analyzer on board RSS spacecraft. The name is HEP. And high energy electron experiments instrument on board RSA observes 70 keV to 2 MeV electrons. And this is the photo of the HEP sensor. And this is the HEP sensor on RSA spacecraft. And the structure of this analyzer is very simple. There is a collimator here. And below the collimator, there are silicon solid-state detectors here. And multiple solid-state detectors are stacked. And the right-hand side photo shows the solid-state detectors. And these detectors are stacked. And this figure shows the principle of measuring energy loss by semiconductor solid-state detectors. And when an electron interacts with the semiconductor detector, electron-hole pairs are generated like this. This is the solid-state detector. And the number of electron-hole pairs depends on the energy loss in the detector. And in this case, E is the electron energy, and epsilon is the average energy to produce an electron-hole pair. In case of silicon, it is 3.6 eV. And when the incident electron energy is 100 keV, and this electron stopped inside this SSD, the generated electron-hole pair is 2.8 times 10 to the 4th pairs. And applying bias voltage here and here, we can measure the generated hole electron pairs. And because the unit charge is 1.6 times 10 to the 19 coulomb, the 2.8 times 10 to the 4 pairs corresponds with the 4.4 femtocoulomb. So we have to measure this small signal to detect the electron energy. And charge sensitive amplifier is connected to this SSD, and we can measure these 4.4 femtocoulombs. And by doing so, we can determine the energy of the incident electrons. And this figure shows the ET spectrograms obtained by HEP instrument on RSS spacecraft. And from here to here, it is 1 day, 24 hours. And we can see that electrons as high as several MeV are observed. Okay. Another example of the high-energy electron sensor is shown here. This is an high-energy electron sensor on board Bepi-Colombo MEO spacecraft. And this is a pin slit type collimator plus solid-state detector with ion rejection foil. And it measures electron energy spectra, and it is developed in ISAS and Nagoya University in Japan. And this figure shows the structure of this instrument. There are 2 SSD stacks here, and electrons come this way from the upper direction and from the lower directions. And each sectors are divided into 5 channels, and we can cover 114 degrees with 10 channels. And it can measure the electrons between 30 to 700 keV. We also have ion high-energy particle detector on Bepi-Colombo spacecraft. And this is the high-energy ion energy. This instrument measures high-energy ion spectra and mass, and it is also developed in Nagoya University and ISAS. And this figure shows the structure of the structure and measurement principle of HB ion sensor. It measures ions between 30 keV and 1.5 MeV. And the incident ions come this way, and there is a very thin carbon foil here, and it passes through the carbon foil. And when it passes through the carbon foil, secondary electrons are emitted like this, and the ions are detected by this SSD placed here. And SSD, when the ions collide with the SSD, secondary electrons are emitted from the surface, and secondary electrons are detected by MCP here. And the timing between the start signal generated by the ion passing through the carbon foil and the stop signals, by measuring the time difference between start and stop signal, we can measure the velocity of the ions. And SSD can measure the energy of the incident ions. So using these parameters, we can determine the mass of these incident ions. So this is the measurement principle of this instrument. So this is the mass spectrometer of high-energy ions. Okay, I will talk about the future development of particle instruments, especially low-energy particle instruments. Okay, for these 10 years, I have been developing low-energy particle spectrometers in order to realize these 3 objectives. One is a higher and higher time resolution, and second is the mass spectrometers for any destinations, and number 3 is miniaturized high-performance analyzers. And talking about the higher and higher time resolutions, this figure shows the time resolution of low-energy particle sensors to measure 3-dimensional distribution function. About 30 years ago, the JOTEL spacecraft low-energy charged particle instrument had 12-second time resolution. And Nozomi spacecraft, we had, this is the Japanese first Mars explorer, but it failed. But it has a plasma instrument, and the time resolution was 8 seconds. And on the Kaguya spacecraft, this is Moon orbiter, we had the plasma instrument, which has the 1 second time resolution. And recently, the United States MMS spacecraft, it has the ion and electron instruments. Well, actually speaking, this ion instrument was provided by ourselves, and it has a time resolution of 150 milliseconds, and electron sensor has time resolution of 30 milliseconds. So the time resolution becomes faster, and in the future, the time resolution will become faster than 1 millisecond. After, well, I'm not sure when it will be, but in the near future. And talking about the mass spectrometers for any destinations, we developed a mass spectrometer for a Kaguya spacecraft that measured moon plasmas in 2007. And after that, we developed another mass spectrometer on Bepi Colombo that will start observation at Mercury magnetosphere in 2025. And this is the this instrument has higher mass resolution than this moon mass spectrometer for a Kaguya spacecraft. And after that, we started to develop a neutral mass spectrometer, and the one is the reflector called the reflectoron, and we made a test model. And after that, we started to design the triple reflection type reflectoron like this. And this instrument will be on board a lunar rover in the near future. Okay. And talking about the miniaturized high-performance analyzers, in the future, we want to realize 50-kilogram microsatellite for fully in-situ measurements of plasma particles and magnetic electric fields. And this is the conceptual design of such an micro spacecraft to make a fully in-situ measurements of plasma particles. And in order to realize this, we have to develop lightweight, rigid booms for the plasma wave measurements. And we also need the boom for magnetometers. And another thing we have to develop is lightweight, small, low-energy particle spectrometers. At present, the size of the low-energy charged particle spectrometer is like this. The size is about 10 centimeter, 10 centimeter cubic, plus electronics box. And the weight is about 1.2 kilograms. But, and the electronics part can be miniaturized using ASICs. But the analyzer cannot be easily miniaturized if we need high detection sensitivity. And now I'm trying to miniaturize a low-energy charged particle spectrometer like this using a metallized plastic. And a test model miniaturized low-energy charged particle spectrometer are being made like this. And it is being tested now. Okay, and if we can realize the 50-kilogram micro satellite that can make fully in-situ measurements of plasma particles and magnetic and electric fields are if this is realized, the formation of light small satellite mission using small launch vehicle like Japanese Ipsen rocket is realized. And far in the future, we'll be able to realize the formation of flying satellite mission in other planets. And in order to realize this, we need international collaboration. For example, one country provides one small spacecraft that is not so expensive. So in the future, we'd like to collaborate with Taiwan also. Okay, so in summary, today I talked about the low particle analyzers. And first I talked about the magnetosphere observation by satellites. And I showed the examples of low energy particle analyzer that is called a spherical analyzer and top hat type electrostatic analyzer. And I also talked about the charged particle detectors, channel tone, and MCP, multi-channel plate. And I showed examples of ion energy mass spectrometer that is top hat type electrostatic analyzer plus time of flight measurement. And another is top hat type electrostatic analyzer plus LEF time of flight measurement. And I also showed examples of high energy particle detector, electron detector, and ion detector. And I showed the development of future low energy particle spectrometer. Thank you very much.
Okay, thanks for Professor Saito's talk. Is there any participant want to ask questions?
Yes, I wonder, for the miniaturization of the last detectors you spoke about, you mentioned that the detector itself cannot be miniaturized much, assuming you want to retain precision and signal quality. So I wonder what exactly, can you describe a bit more in detail of what hinders miniaturization?
Okay, because the incident area cannot be miniaturized. If we want to realize the high sensitivity, what we can do is to develop a very thin analyzer. Thin analyzer means the volume is small, but the incident area is large. In order to do so, one way is to develop a very small analyzer and stacking these analyzer in two-dimensionally. So that is one way to develop such an thin but large incident area analyzer. So that is what we are doing now. This is the very small, tiny analyzer here. And by using these 4 elements, we can stack these elements as much as we like. By stacking, we can make the thin but large area instrument. So this is what I'm doing now.
Okay. So when you stack to multiple layers, do you then have to compensate for some kind of biasing effect, or do you get like detection degradation on a lower layer or on a buried layer that is underneath, and essentially a layer of detector that is in front of one of the lower layers? If that kind of
sorry,
sounds
lower
confusing.
layers means what? Will you please explain more?
Okay, so I wonder if you stack multiple analyzer layers on top of each other. In other parts of semiconductor design, we usually end up with some form of biasing or some form of influence, essentially accuracy impact or detector impact on lower layers that are being covered.
Sorry.
Do you have this issue here too?
You're talking about the semiconductor detector. Now,
yes.
Okay. This is a low energy particle instrument. So this instrument doesn't use the solid state detector. And talking about the instrument using solid state detector, those instruments can be miniaturized rather easily. But the difficult point is that in order to make this kind of low energy particle instruments, it needs some structures like electrostatic analyzer. So that is the difficult point to miniaturize. So my answer to your question is that this instrument doesn't use solid state detector, so we don't care about that.
Okay, thank you very much. That's quite enlightening.
Thank you.
Okay, is any participant have questions? Oh, Professor Saito, I have maybe very basic questions.
Okay.
Because theoretically, if we want to measure the neutral particles, the very simple, just simply remove the charged particle and then make the neutral particle to be charged.
Yeah.
And then we can follow the similar way to measure the charged neutral particles. So what is the main, but as we know now, the measurement to neutral particle, the experiment is very, very few. What is the main challenges to for such kind of neutral particle measurement in space plasma experiment?
Okay. Well, now we are developing neutral mass spectrometer, and well, there are several kinds of neutral mass spectrometer. One is to measure neutral atmospheric neutral mass, and another is the surface element of the planets. And talking about the neutral mass spectrometer to measure atmospheric particles, that instrument has to measure the neutrals coming from any directions. And those neutral particles should be ionized using some way. And we are now developing the ionizing part of the neutral particles. And in order to efficiently ionize the neutral particles, we need some good ionization source. And that is one thing we have to carefully make development. And there is some lifetime of the ionized part. So we have to select carefully the materials of the filament and so on. And it consumes much power to generate enough ions. So the efficient, the ion source with high ionized ratio should be developed. And that is one thing to develop. And talking about the mass spectrometer for surface element mass spectrometry, well, the mass resolution should be quite high. In order to do so, we carefully design the mass spectrometer structure. And for example, this analyzer used for to be used for lunar rover, it has high mass resolution as high as 100 or 200, and the mass spectrum should be very clear in order to distinguish the very near mass species. So that part is the well, a difficult point. Okay.
Okay. Thank you very much. Is there any participant want to ask questions to Professor Saito's talk? Okay, if no further questions, so let's thank our speaker today, Professor Saito, to give this very interesting and very good talk to about spatial instrumentation. Thank you very much.
Thank you very much for providing me with this very valuable opportunities. So thank you very much.
Yeah, thank you very much. Okay, bye.
Bye.